Okay, let's review Chapter 4 by looking at some old test problems that should help you with test and homework problems. Sections 4.1 and 4.2 are very similar to 1.1 and 1.2. 4.1, you need to learn how to write the Lagrange polynomial degree n that passes through a given n plus 1 points. In Section 2, the main thing to remember is this formula for the error in the Lagrange polynomial, or the polynomial degree n. There's only one. Lagrange is just one way of writing it, but so the unique polynomial degree n that interpolates to f at n plus 1 points, z0 through zn, that's n plus 1. And the error is, it looks a lot like the Taylor remainder formula, except Taylor has x minus 1 point to the n plus 1 power because it interpolates at 1 point n plus 1 times, whereas Lagrange interpolates at n plus 1 different points 1 time, so it has x minus each of these. The error's got to be 0 at each of those points. Otherwise, it looks the same: n plus 1 factorial, n plus 1 derivative at some unknown point. Assuming x is between the first and last points, so is that, and that's all you can say. So this is important for Section 4.2. You just need to know that formula. Section 3 on cubic splines, main thing is to remember that s prime, and s double prime are continuous at all the knots, and it's a cubic polynomial in between in each strip. So let's look at some old test problems. Here's a typical Section 4.2 problem. Says if you have a polynomial degree 2 that interpolates to 6 over 1 plus x at 3 points. It doesn't ask you to write that polynomial, but that's certainly one question could have asked. But this case, it only asks you to get a bound on the error at 0.15, which is halfway between the second and third points. So you just need to remember the formula for the Lagrange error polynomial degree n equals to 2. It involves the third derivative at some point between, since x is between 0 and 0.2, so is c, psi, whatever that is. So it involves the third derivative, n plus first derivative, or n plus 1 factorial time x time minus each one of those, 0, 0.1, and 0.2. And in this case, it asks you for a bound on the error at a particular value of x. That's good. Then you just have to plug that value of x in, and then all you have to worry about is getting a bound on the third derivative, which is minus 36 over 1 plus x to the fourth power. And so the third derivative at this point, all you know about it is between 0 and 0.2. It's not 0.15. It's anywhere between 0 and 0.2. So the biggest it could be is when, if you assume it's 0, so just be minus 36, absolute value is 36, divided by 3 factorial, just plug in x equal to 0.15 and grind it out. Now, in some problems it will say, it won't give you a specific value. It won't say find a reasonable bound on the error at this specific point. It'll say a bound that's good for any x between 0 and 0.2, and that makes the problem a little harder, as we'll see. Okay, here's a couple of little harder problems involving polynomial error bounds. So you have a polynomial degree 3 that interpolates to cosine of 3x at 4 points, where h is not specified, minus 1.5h, minus 0.5h, 0.5h, 1.5h. It says get a reasonable upper bound on the error between the very first and last point. So x is not specified. X could be any point between minus 1.5h and 1.5h. So, well, first you need to remember the error bound n is 3, so it involves the fourth derivative of alpha over 4 factorial, x minus each of the 4 points. And the fourth derivative of cosine of 3x, every derivative you get a factor of 3, so after 4 derivatives you're back to cosine, but you've got a 3 to the fourth. So that's not really any different than the Taylor polynomial. Getting a bound on the n plus first derivative is pretty much the same as it was Chapter 1. It's this getting a bound on this that's hard when x is not specified. So, well, it says here you can be lazy and just say, well, x is between the first and last points, between this and that. Therefore, x minus each of those points is less than 3h, because the distance from x0 to x3, the whole distance of the interval is 3h. X is somewhere in there, so x minus any one of those 4 points is less than 3h, so that's kind of a lazy, but it gives you an upper bound, so you just say, well, each of these is less than 3h, and cosine of anything's less than 1, so that's less than 3 to the 4th times 3 to the 4th times h to the 4th over 24. But then the second part is the hard one, but it's for extra credit, notice. And don't usually give a problem like this. In fact, this is similar to a homework problem that I used to assign and don't now, so probably wouldn't give one like this, but it's interesting anyway. So it says, same question, but now don't be lazy. Try to get the best possible bound on this. And this is why it's, I usually tell my students, well, it's okay to be lazy because it's too hard to not be lazy on this. In other words, the lazy way is to just say, as we did, that x minus any one of those 4 points is less than the total distance 3h from the first to the last point. Of course, it's a lot less than that for some of them, but that will give an upper bound anyway. But now it says, okay, now don't be lazy, get the best upper bound possible. So x0 is minus 3/2 h minus 1/2 h over 2, 3/2 over h. So you're trying to get a bound on this. Again, if you were given a value of x, you just plug it in, it'd be easy. But x is anywhere between minus 3/2 h and plus 3/2 h, and it says get the actual smallest upper bound you can, which is usually pretty difficult to do because basically this is a polynomial of degree 4, and it's kind of hard to find the absolute maximum, but in this case it's possible. You take this and that, multiply it out, this and that, and you get this, and then you say, well, that's a polynomial of degree 4, it's going to have a maximum at, it's actually 0 at the first and last point, and at 4 points, including the first and last, what's the biggest it can be? And well, finding the maximum of polynomial degree 4, you take the derivative, set that equals 0, and you find that x equals 0 and plus or minus the square root of 5/4 h. So that's this point is between the second and third. These are between the first and second and the third and fourth, but they're not exactly in the middle. So the maximum has to be at one of those 3 points, so you just evaluate it at each of those points, and you find that the largest is at these 2 points, namely minus h over 4. So being lazy, we got 3h to the 4th power. Working a little harder, we just get h to the 4th, and so we cut the bound by a large factor there, a factor of 81 actually. So both of these are correct. In other words, the error is guaranteed to be less than both of these, but the smaller the error bound is, the better. But it's usually not worth that extra work. Both of them are order h to the 4th, which is usually all we're interested in. Okay, here's another, notice we use the Lagrange error formula a lot here. Polynomial degree n, which interpolates to cosine of 3x at n plus 1 uniformly spaced points between 0 and pi. Remember, we actually did that experiment with exactly that function in points between 0 and pi. Get a bound on the maximum error. Well, n is left general here. Usually we specify a degree of the polynomial, but it's for general n. So n plus first derivative at some point between 0 and pi, since x is between 0 and pi. This has to be there also over n plus 1 factorial times x minus each of those points going from 0 to pi. And we're being lazy here. The n plus first derivative, well, every time you take a derivative, you get a factor of 3. So after n plus 1, you'll have 3 to the n plus 1 times either cosine or sine of 3x, and either one, cosine or sine, is less than 1. So the n plus first derivative is less than 3 to the n plus 1 over n plus 1 factorial. And now, if you be lazy, you say, well, x is somewhere between the first and last points, which are 0 and pi. So each of those differences is less in absolute value than pi. So the n plus 1 of them is less than pi to the n plus 1. So put it all together, you get 3 pi to the n plus 1 over n plus 1 factorial. And then it says, will your bound go to 0 as n goes to infinity? Yes, because the numerator goes to infinity with n, So does the denominator, but we know from calculus 2 that the factorial goes to infinity a lot faster than any power, than n plus 1 power of any constant, no matter how large. So eventually the denominator wins out, so it does go to 0. So theoretically, you're guaranteed that the bigger n is, the better your high degree polynomial will do. Although we saw that in practice that round off error takes over when n is large, and that's all not true. And here's a 4.3 problem. Cubic spline, 3 strips, less than 1, between 1 and 3, and greater than 3. And it just says what do the letters have to be for this to be a cubic spline, which just means that this cubic and that cubic at the point where they meet, namely 1, have to have the same value, same first derivative, same second derivative. The second and the third cubics, the second strip and the third strip, those cubics, actually notice this one is a quadratic. The leading coefficient is of x cubed is 0, but when I say cubic, I usually mean cubic or less. So that's still a cubic spline there. Well, piecewise cubic anyway. So these two cubics have to have the same value, same first and same second derivative. You set these two equal, these two equal, these two equal, those two, those two, those two, solve, and you get that A, C, and D have to be anything, but they can be, A can be anything, but C and D have to be the same. And looks like B and E can be arbitrary. Notice it doesn't say a natural cubic spline, just cubic spline, and it doesn't say it has to interpolate it to certain values. It just says cubic spline. It doesn't specify what the values of F have to be at 1 and 3. Here's a true-false question. It just says that if S is a cubic spline, then S, S prime, S double prime, and S triple prime must be continuous everywhere. That's false. S, S prime, and S double prime have to be continuous everywhere, but not third derivative. If the third derivative are continuous, then it'd be the same cubic everywhere, because the cubics only have 3 derivatives. The fourth derivatives are 0 everywhere. Okay, this is a 4.1 problem, and that's 4.2. Says if F has these values, write, well, use cubic interpolation. In other words, write the Lagrange cubic polynomial that interpolates those 4 points and evaluate it at 10.5. In other words, halfway between that and that. Well, fortunately, only one of the F's is non-zero, so that's the only one, that normally there'd be 4 terms. The first one is F at 10 times x minus everything except 10 over 10 minus everything except 10. But the other 3 terms are 0 because F is 0 at those, so this is all there is. And you don't need to multiply it out to get the actual cubic. Just plug in 10.5 for x, grind it out, and you get this. And then the next part says, well, we didn't say what F is, but suppose you know that the fourth derivative is less than 0.05 in absolute value for all x, then bound the error in your approximation here. Well, the error is less than the n plus first fourth derivative at some point over 4 factorial times x minus each of those points. Is given that the fourth derivative is always less than 0.05, so just say it's less than 0.05 in absolute value over 4 factorial, and then you just plug in x equals 10.5, and the error is guaranteed to be less than that. Now, this is an interesting test problem that was not very popular, as I recall. Hardly anybody got it right, but it's worth looking at. A quintic spline, that means a 5th degree spline interpolant. So we've been talking about cubic splines, but you could have a 5th degree spline, which is a polynomial degree 5 or less in each interval, and passes through given points, and is continuous and has continuous first, second, third, and fourth derivatives. So cubic splines are continuous and up through the second derivative, everything except the third derivative, which is the highest they have. The quintic, highest derivative it has that's not 0 is 5th derivative. That doesn't have to be continuous, but up through the fourth derivative is continuous. So it says how many unknown coefficients need to be determined. If we were trying to actually find the quintic spline, which is up through fourth derivative continuous and interpolates to these points, how many unknown coefficients need to be determined? This basically the same analysis we did for the cubic spline, but for a quintic. Well, the fifth degree spline has 6 coefficients, and there's n strips, so 6n coefficients to be determined. How many interpolation conditions are there? Well, there's 2n, because in each strip your cubic has to pass through the 2 endpoints. And how many continuity conditions are there? Well, S is automatically continuous, so you don't need to require that, but S prime, S double prime, S triple prime, and S fourth are not automatically continuous, so you have to require that those 4 be continuous at the n minus 1 interior points. So 4 times n minus 1. And then it says, okay, so you got 6n unknown coefficients, 2n interpolation conditions, 4n minus 4 continuity conditions. So you've got 6n minus 4 equations to determine 6n coefficients. That's not enough. You need 4 more conditions, 4 more n conditions. For example, you could require that S prime and S double prime both are equal to the F prime and F double prime at both n conditions, or something like that. So the cubic spline needs 2 n conditions, the quintic spline needs 4 n conditions to pin it down. Okay. Okay, this is a problem. F is sine of pi x, and these are the values of sine of pi x at those 3 points. We actually already did this problem in a previous video, so but part A and B we did, so I guess I could skip this. You write out the polynomial of degree 2, which interpolates at these 3 points, and only the middle term is non-zero, because f of 1 and f of 2 is 0. F of 1.5 is minus 1. You have x minus everything except 1.5. You plug in 1.6 and you get minus 0.96, which seems reasonable. And then it says get a bound on the error, and we did that last time. It involves the third derivative, and at 1.6 we get a bound of 0.124. So we already did those 2 parts. So now the third part says, you can actually evaluate that polynomial. Well, we did it here. And you can actually evaluate the function sine of pi x at 1.6. So what's the true error? Well, the true error is 0.009. Our error bound was 0.124, which is a whole lot larger. Well, that's we didn't claim that was the error. We just claimed it was a bound on the error. It's a pretty large upper bound, but it is we guaranteed the error is less than that, and in fact it's quite a bit less. Okay, here's another 4.1 problem. They're all pretty similar. Polynomial of degree 3 passing through those 4 points. You write it out. Normally there's 4 terms, 1 for each value of x, but only 2 of them are non-zero. So the second one, f of 110 is 3, and then you have x minus everything except 110 over 110 minus everything except 110. And they, first and third terms are 0. The second and fourth are non-zero. 1 times x minus everything except 130 of 130 minus everything except 130. And says use this to interpolate at 125, which is halfway between the last 2 points. So you just plug in x equal 125, you get minus 0.625, and then get a bound. You can pretty predictable what I'm going to ask next. Get a bound on the error. If I didn't specify what the f was, but I'm telling you that its fourth derivative is less than 0.001. So fourth derivative is less than 0.001 over 4 factorial x minus each of those points. X is 125, so there's the bound on the error. And here's a section 4.3 problem. It just says to define a natural cubic spline, and it's a cubic polynomial in each strip. S, S prime, S double prime are continuous. Oh, a natural cubic spline. And natural cubic spline means the end conditions are the second derivative 0 at the 2 endpoints. So just definition of natural cubic spline. Here's a true-false question. If f is a smooth function and Ln is the Lagrange polynomial that interpolates to f at uniformly spaced points, n plus 1 uniformly spaced points between a and b, Ln is guaranteed to converge to f as n goes to infinity, and ignore round-off error. That's false. We saw, for some functions it's guaranteed, but for the Runge function it doesn't appear to converge at all and doesn't in fact. So that's why high degree polynomial is not a good idea, even if you didn't have to worry about round off error, which you do.